Hi everyone. In today's lesson, section 4.5, we will discuss common and natural logarithms. Common logarithms are logarithms with a base of 10. They get this name from the fact that a logarithm with a base of 10 was used so frequently that people got tired of writing the 10 there. Much like when we see a square root, we don't see a 2 written as the index number because square roots are used so frequently. So log base 10 of x, which would be a common logarithm, is going to be written just as log of x. You just won't see the base number written there. So from now on, if you see a logarithm and it doesn't appear to have a base number, you just assume that it's a 10. So the common log of 1,000 would be equal to 3, because in exponential form, you would have the base of 10 raised to the third, and it's equal to 1,000. The common log of 100, likewise, would be 2, because 10 squared is 100. And log base 10 of 10 is equal to 1. Anytime the base number matches what you're taking the logarithm of, the result is going to be 1. And again, it's because 10 to the first equals 10. The next column, the common log of 1 is equal to 0, because remember, anything raised to the 0 power is 1. Common log of 0.1 would be equal to negative 1, because that would give us 10 to the negative 1, which would be rewritten as a fraction, 1/10, and 1/10 is equal to 0.1. All right, the common log of 0.01 would be equal to negative 2, because it's 10 to the negative 2, or 1 over 10 squared, or 1/100th. 0.01. Y equals the common log of x, and y equals 10 to the x are inverse functions. And to just show you this, it's because if you have y equals 10 to the x, and you want to find the inverse, you would switch the x and the y, and then you would solve for y. Well, the way in which you would solve for y is to write this as the common log, or log base 10, of x, and it would be equal to y. So that's how I'm coming up with this equation right here. Right. If you did a composition of the two functions, meaning we did f of g of x, we would come up with log of 10, common log of 10, to the x power would be equal to x, and 10 raised to the log, or common log of x, is equal to x. Right, so basically, what you see in the box are just a couple of rules. Anytime we have the log with the same base as what we're taking the logarithm of, the answer will always just be the exponent. It's no different if it's a common log. You just don't see the base of 10 written there for you. Likewise, if we take and we raise our base of 10 to a common log of x, the answer in here will always be what you're taking the logarithm of. Okay, so if it were 5 to the log base 5 of x, this would also be equivalent to x. So just thinking about these two as properties allows us to evaluate everything in example 2. The common log of 10 to the 4th is just equal to 4. So it's log base 10 of 10 to the 4th. We have a match for these two numbers, so the answer is the exponent. You could also rewrite it with the 4 out in front and see that it would be 4 log base 10 of 10, or 4 times log base 10 of 10, which is equivalent to 4 times 1, which is just 4. Okay, so knowing that, we don't have to go through all of that other stuff again if you just accept that property. So down below, the common log of 10 to the negative 3 halves is just going to be negative 3 halves. And that's it, just that exponent. All right, to the right, we're going to be using the second example, if you will. 10 to the common log of 14 will just be equal to what we're taking that logarithm of, which is 14. I know I don't like to say things this way, but when you have 10 to the common log of a number, I almost want to say to you, think of these two as canceling each other out, although it's not exactly what's happening here. But the answer, again, is just what you're taking the logarithm of. So the one down below, 10 raised to the common log of the square root of 2, the answer would be the square root of 2, what you're taking that common log of. All right, in example 3, these are just calculator questions. So if you go to your calculator, and it depends on which version you're working with, but most scientific calculators have a key that just says log on it. Okay, so on the scientific calculator in the classroom or little blue calculators, I'm not exactly sure where it is on the keypad because I don't have one here at home with me. On the graphing calculator, it's on the left-hand side of your keypad. Right, so that is just the common log key. All right, so when you go to do the log of 10,000, you would press the log key and then type in 10,000. And then you're going to hit enter. Started an extra 0 there. And we know that it should come back to be 4 because we did that one earlier. All right. For the rest of these, we're going to have to round to 3 decimal places. So when you do the log of 2.5, it comes out to be approximately, so that's why I have the wavy equal sign, 0.3979. Okay, so that's going to round to 0.398 to 3 places. The log of 1/3, you just have to make sure that you put the 1/3 in parentheses. So you're going to press the log key on your calculator, parentheses 1 divided by 3. And it works out to be approximately negative 0.4771. All right, to 3 places, just negative 0.477. All right, with this last one, hopefully you didn't go as far as typing it into the calculator. You have a negative number here, so there's no solution. Right? Logs are always going to be positive because the base of a logarithm is always positive. If you did go to the calculator, you would see an error message. All right, or something like that. Different calculators say different things. Let me just try it on my calculator. Yep, mine says error, non-real answers, okay? And again, that's because you're taking the logarithm of a negative number and it's impossible, right, to raise a number to an exponent and have it, raise a positive number to an exponent and have it turn into a negative. So just make a note that you can't take the logarithm of a negative number. All right, natural logs are logarithms with a base of e. Now, you may not have encountered the number e before, but it's a mathematical constant, also called Euler's number. Some people may call it Euler's number. E is approximately equal to 2.71828, so on and so on and so on. Very similar to pi. Pi is also a mathematical constant that you're familiar with. That number e is used in many applications in finance, exponential growth and decay, measuring earthquakes, like measures of magnitude, and for instance, in the size of the universe, calculating the size of the universe. All right, for us, what we need to understand about natural logs is that when you see ln, that's a logarithm with the base of this number e. Now, if you do a little searching on your calculator, around where you found the logarithm key, you should also see a natural log key. Right? So if you press ln of 3 on your calculator, I'm going to play along here. So ln of 3 on the calculator. We're going to approximate this to 3 decimal places. So natural log of 3 would be approximately equal to 1.099. Okay, and that's because e to the 1.099 power is approximately equal to 3. Also in your calculator, you should be able to find e. Usually it's, well, I don't know about the blue scientific calculators, but on my graphing calculator, it's above the division sign. So when I press second and divide, I get an E on my screen, and when I hit enter, it just shows you a few more places of Euler's number, and you're going to notice this one seems to have a little bit of a pattern to it. All right, try the natural log of 1/2 on your calculator. So natural log of 1/2, or you could type in 0.5, and that's going to be approximately negative 0.693. And again, that's because e raised to the negative 0.693 power is approximately equal to 0.5. All right, so just keep in mind that if we have a logarithm with a base of e of some number x, that gets rewritten as the natural log of x. That's the only difference, okay? So what you're learning about today are 2 different specific logarithms. So everything that you've learned so far, all the properties, still the same, okay? It's just the base is different. So ln just means it's a logarithm with a base of e. So much in the same way that we had the 2 things that were inverse functions for common logarithms, we have y equals ln x and y equals e to the x are inverse functions. So by composition of inverses, we get property number 1 and property number 2 below. Same thing that we were doing before with common logs. If you're taking the natural log of e raised to some power, then your answer is just going to be that exponent. So for instance, the natural log of e to the 5th would just be 5. And that's because e to the 5th equals e to the 5th. E raised to the natural log of x will just be equal to x because it's e raised to the log base e of x. I remember what I said. In this particular case, your answer is just what you're taking that logarithm of. The natural log of e is equal to 1. Think of it as log base e of e equals 1. E raised to the 1st will be equal to e. And finally, the natural log of 1 is equal to 0 because this will be log base e of 1. It's got to equal 0 because e to the 0 power is equal to 1. So in example 5, we are just simplifying these using those properties of natural logs. So when we're trying to simplify, we want to do some rewriting. So this one, natural log of 1 over e, would get rewritten as the natural log of e to the negative 1. So I'm getting it out of the form of a fraction, so that exponent becomes negative. And then we're using our very first power right above to say the answer would just be the exponent, negative 1. All right, this second example, keep that 1/3 The natural log of 1 you have right up here. Natural log of 1 is equal to 0. So 1/3 times 0 is 0. And the next example, the natural log of e to the 5th is just going to be 5. Again, if you needed to, you could rewrite it as 5 natural log of e. And natural log of e is just equal to 1. So it would become 5 times 1, which is 5. All right, this last one is all set up for you to do exactly that. 4 natural log of e is 4 times 1, which is 4. So as I mentioned before, all the properties of logarithms that we learned before apply to our natural logs. So the natural log of m times n can be expanded using addition. So it would be the natural log of m plus the natural log of n. Division would become subtraction, so it would be the natural log of m minus the natural log of n. Anytime you have an exponent, it can be rewritten out in front, so this would be k times the natural log of m. And this last one is just a property of equality. If the natural log of x equals the natural log of y, the only way that this can be true is if you're taking the natural log of two quantities that are equal to each other. Okay, so like we did with logarithms, like common logarithms or regular logarithms with different bases, they're going to use the properties of logs to expand each expression. So the first thing that I would do is look at this division. I would use that property first to rewrite it using some subtraction. I think the key to this is not trying to do too many things at once. Okay, so that's why in my notes in here, you're going to see me do basically one thing at a time, but sometimes, I'll explain if I'm going to do two things at once, which actually I'm going to do just now. All right, so I rewrote it, that division as subtraction, and now I know I want to move these exponents out in front. So I've got an exponent here and here, but I see this guy, that square root. So, and I also know that I need to expand using addition because I've got that multiplication. So kind of a lot to think about. So let's keep the expansion going by expanding that multiplication using addition. So make it natural log of x to the 4th plus natural log, and I'm going to do a second thing. I'm going to rewrite that with a rational exponent. So I got rid of the square root and I wrote y to the 1/2 because raising something to the 1/2 power is the same thing as taking the square root of it. And then we would still be subtracting the natural log of z to the 5th. All right, now we're going to deal with all those exponents. Take all of those exponents and put them out in front, and then we'll be done. So it'd be 4 natural log of x plus 1/2 natural log of y minus 5 natural log of z. And that's it. You've done as much as possible to expand it. There's no more multiplication, no more division, no more exponents. Okay, part B, it's a little different because we're taking the log, and this is just a common log. All right, the base is 10. It's not there, so we assume it's a base 10. And we have this whole quantity that's inside the radical. So we're going to rewrite that with a rational exponent. So it's going to be the common log, or just log, of the quantity x to the 3rd times x squared plus 3. All right, what we're going to do is move that exponent out in front first. So I want you to write it as 1/4, and then give me some brackets, because it's going to apply to everything inside. All right. So again, I am going to do a second thing here. So moving the exponent out in front just clears us to take care of this multiplication. So expand using addition. write it as 2 logs. All right, and then we're really going to take 2 more steps. I want to rewrite it with this exponent right out in front, right there. So it's 1/4. Still have the brackets, and then 3 log of x plus the log of the quantity x squared plus 3. Now, I can't move this 2 out in front because there's plus 3, and I can't expand that any further. Addition doesn't expand into more addition. That's not a property, so we have to stop with that piece there. All right, but what we can do is distribute this 1/4 now to both of those. So 1/4 times a 3 becomes 3/4 log of x, common log of x, plus 1/4 common log of the quantity x squared plus 3. And we're done. That's it for the expansion. Okay, so again, multiplication expands to addition, division expands to subtraction, but if you had addition or subtraction in the problem, it can't be expanded any further. Okay, so now we're going the other way, right? We're going to use the properties of logarithms to condense each of these. So no common logs or natural logs. These are just 2 good practice problems. So the first thing we want to do is take those exponents and put them onto the variables, okay? So before we try to smush anything together, we're going to rewrite it as log base 3 of x to the 3rd plus log base 3 of y to the 4th minus log base 3 of z to the 5th. Okay, now we have the same base, all right, in all 3 of our logarithms, so we know we can keep condensing. Here, this is addition, so that would condense using multiplication. So it's log base 3 of x to the 3rd times y to the 4th minus log base 3 of z to the 5th. And now we have that subtraction, and subtraction gets rewritten using division. So it's going to be log base 3, and then I want to make a fraction, and we're going to put x to the 3rd, y to the 4th in the numerator, and put z to the 5th in the denominator, and that's it, other than putting it all in brackets. So we know we're taking the logarithm of all of that. Okay, so this one also has to be condensed into a single logarithm. So we're going to start by distributing this 1/2 to both of those terms. Okay, so again, I'll try to take it one step at a time. So we're going to have quite a few steps in here. We have 1/2 log base 4 of the quantity x plus 1 minus, it's just going to become 1 because 1/2 times that 2 is just 1. So I don't need to write anything. You could write a 1 there if you wanted to, but it's minus 1 log base 4 of x minus 1 plus 6 log base 4 of x. Okay, so we got rid of the brackets. Now we're going to do what was our first step on part A, and that was to take the exponents and put them onto our variables. Okay, so this first term would get rewritten as log base 4 of x plus 1 in parentheses raised to the 1/2 minus log base 4 of x minus 1. No exponent to bring up there because it's a 1. Over here, log base 4 of x to the negative 6. Sorry, x to the 6. I don't know where that negative came from in my head. Let me erase it completely in there. Okay, I think we're all set now. Now, we're going to do this in a couple steps. First, we have subtraction here. That has to become division. So it would be log base 4 of x plus 1 in parentheses to the 1/2 divided by x minus 1 in parentheses. And to that, we're adding log base 4 of x to the 6th. Well, when it's addition, it condenses using multiplication. So this is going to become log base 4 of x to the 6th times x plus 1 to the 1/2, all divided by x minus 1. Now, a couple things. You could have put the x to the 6th behind, but what I'd like to do finally is rewrite this part, because it's x plus 1 raised to the 1/2. Hopefully you remember that that would be rewritten as the square root of x plus 1 all over the quantity x minus 1. Now don't go crazy on me trying to simplify it. It cannot be simplified. You don't have a common factor that you can divide out of every term.